Hi everyone, I'm Güvenç, and today I will talk about the red black tree topic. And before we jump into the red black trees, let's first understand what a tree actually is because it's simpler than you think. And it's also very important to learn the basic before we move on. So let's look at these tree diagrams. They look different, but they're actually the exact same structure. First one, a family tree. You got grandpa at the top, then the next generation below, your parents and uncles and aunts, and below that, you, the grandchildren. The key idea, one person at the top, and that's it, that's the root. And everything branches downward. Each person can have at most two children in our simplified version. So, second one, let's think we got a company. And at this company, CEO sits at the top. Managers report to the CEO, and individual employees report to the managers. Same exact shape. Root at the top, branches going down. And the third, the computer science version. Same thing. We got a node A, the top, that's our root. B and C are its children. D, E, F, G are the leaf nodes. They have no children. So here is the key insights. All three of these are the same data structure. A binary tree is just a hierarchy where each node has at the most children, a left child and a right child. That's it. This is simple rule is what makes everything as possible. So let's move on to binary search tree, the BST. So a regular binary tree just stores values, but binary search tree adds one brilliant rule. Left child is always smaller than the parent. Right child is always larger. So let's look at this tree. Root is 30. Everything on the left, 10, 5, 20, they are all less than 30. Everything on the right, 50, 40, 60, it's all greater than 30. And this rule applies at every single node, not just the root. So let's look at this search trace. So why does this matter? Let's say we want to find number 50. And for the find the number 50, step one, we start at the root, which is 30. Is 50 equal to 30? No. Is 50 greater than 30? Yes. So then we move to right. And after that, we check is we are at the node 50. Is 50 equal to node 50? Yes, 50 is equal to 50. Then we find it. That's only two steps, and there is no there and um, here is the crazy part. Even if we had 1,000 nodes, we'll only need about 10 steps. A million nodes, about 20 steps. That's the power of all log n. Like for real world example, you can think of it like a phone book. You don't read every page from the beginning. You open the middle, you check if you're going too far or not far enough, and keep halving. And that's exactly what BST does. So BST sounds amazing, right? But there's also a massive problem. Let's watch what happens when we insert values in sorted order. 1, 2, 3, 4, 5. Every new value is bigger than the last. So it always goes to the right child because it's bigger than the last. And what do we end up with? So what's gonna happen? A straight line going down to the right. So this is no longer a tree. It's a LinkedIn list. And a LinkedIn list means if we want to find a number, f- let's say find the number five, we have to check every single node from the top. One, two, three, four, five. That's a five steps, five nodes, four or five nodes. For 1,000 nodes, it means 1,000 steps. That's a ON, and it's very bad. We completely lost the O log n advantage. So the question becomes like, how do we prevent this from happening? How do we make sure the tree stays balanced no matter what order we insert values? And that's the exactly why the red black tree exists. So let's move on to red black tree now. So let's learn what is a red black tree. Red black tree is a self-balancing binary search tree. It has all the same BST properties, left smaller and right larger, but it adds one extra thing. And this is every node gets a color, either red or black. That's it. Just we're adding extra color, red and black. Like we can think of it like there is a like escalators in a shopping mall. If everyone crowds to one side, the escalator tips over. But if there's a smart system that automatically distributes the people evenly, left and right, it stay balanced. That's what the color rules do for our tree. So let's learn these five rules for getting more information about these red black trees. Rule 1. Every node is either red or black. Simple, just a color label. Red or black, that's it. Rule 2. The root is always black. No exceptions. Think of it like as the boss always wearing a black suit. So root, the top, always gonna be black. That's it. That's the basic. And rule 3, all nil leaves, meaning the empty spots where there are no children, they count as black. So empty spaces like this is empty, there's no children, it's nil. And we count it as a black. This is important for the math to work. So let's move on to rule 4. If a node is red, both of its children must be black. In other words, no two red nodes in a row ever. Let's look at this example. The red node has two black children. That's valid. But over there, as and if you can see it, red one with a red child. That's a violation. It's broken. It can't be happen. So there is no red parent with red children. So there is not same color for the red as a child. So let's move on to rule 5. Every path from the root down to any nil leaf must pass through the exact same number of black nodes. This is called black height. And if we look at these examples, let's look at this pet A. Pet A goes to the 13. So from 13, then 8, then nil, There's two black notes. 13 is black, 8 is red, so it doesn't count, and nil is black. But we count from the root. So let's look at the pet B. Pet B goes 13, then 17, then nil. Also two black notes, both equal. That's what keeps the tree balanced. Before we get into insertion and deletion, let's understand the simplest fix the tree can do. Just changing colors, no restructuring needed. So for this color change, we can think that as like imagine a company where employees wear color badges. Red for juniors, black for seniors. If two juniors end up working together without a senior between them, HR doesn't recognize the whole company and they just swap badge colors and then the problem is solved. So here is a worked example. We have wallet tree. 10 is the root, colored black because root is always black. 5 and 15 are its children, both red. All 5 rules are satisfied. Now let's insert the 3. Now we insert the 3. Since 3 is less than 10, it goes left. And 3 is less than 5, so it becomes the left child of 5. And always remember, new notes are always inserted as red. That was our rule. And when we check the connection between 5 and 3, note 5 is red. And its new child 3 is also red. There's 2 reds in a row. So the rule 4 is broken. So what we're gonna do? So we check what color is the uncle. So when we check the uncle, the uncle is 15. So how we can know this is uncle? Let's say this is our this is us. The 3 is us. This is our dad, and this is our dad's father, and that's the our grandfather's son. So it means it's your uncle when we think as like a family tree. So when the uncle is red, we can fix this just by recoloring. So parent 5, red becomes black. Uncle 15 becomes black, and grandparent 10, it was black, then it becomes red. But now the issue is 10 is black, 10 is red, and 10 is the root. So rule 2 says the root must be black. So we just flip back to 10, the black. That's it. We just flip back it. And after the changing the root color, we are done. All 5 rules satisfied. No rotation needed and no other things needed, just the color changing. That's the beauty of recoloring. Sometimes the fix is just flipping colors up to 3. So when we just always remember the rules, the basic rules is too easy. Now let's move on to rotations. A rotation is an O1 operation and it only changes 2 pointers, but it fundamentally changes the shape of the tree. And the beautiful thing, it always preserves BST order. The left child stays smaller, right child stays larger. There are 2 types and they are exact mirrors of each other. Left rotation and right rotation. Let's look at the left rotation first. When we left rotate on node 20, what happens is third right child climbs up and then becomes the new root. 20 steps down to the left, and 25, which was 30's left child, moves to become 20's right child. And look, BST order is perfectly preserved. 10, 20, 25, 30 for the exact same order before and after. Just 3 pointer changes. That's it. Now let's look at this right rotation. Is the exact mirror. Now the third is the parent. And 3 leans too far left. We right rotate on 30. So the left child 20 climbs up 30 steps down. And the right, and after that 25 moves from 20's right to the 30's left. And that's how we rotate it. And also here is a like quick comparison that I can say. The left rotation, the right child goes up. Right rotation, the left child goes up. Both are O1. Both preserves BST order and they are exact opposites. If you left rotate and then right rotate, you're back to original tree. They undo each other. And also for the rotation, if you get struggle with it to think the rotations, you can think is like this. So as an example, let's say we're gonna rotate to the right. So we can think it like this. If we drop the top, this drops to right, and this becomes to up. We can think this as like this machine when the buildings. So the top goes down, the bottom of the top comes up. That's it. And it becomes like this triangle. It's same also for the left. When the up one drops, the bottom one comes to up like this. It's like a, you can think of it as like a physics class stuffs. So let's move on. So, all right, let's move on to search. Search is actually the easiest operation. And here is the good news. It works exactly like the regular BST research. You completely ignore the colors, red, black, doesn't matter, just compare and go left, right. So it's like the number guessing name. Is it 50 too low? Okay. It's between 51 and 100. Is it 75 too high? No, it's between 51 and 74. Every guess cuts the range in half. So let's search 15 in this tree. Three simple rules. If the k equals to node's value, found. If the k is smaller, go left. If the k is larger, go right. So let's move on with step one. Let's start at root 20. For the, let's say search for key 15. Step one, let's start with the root, it's 20. So 20 is smaller than the, 15 is smaller than 20. So we go left. Now we are at node 10. 15 is greater then 10, so we go right. And now we are at the 15, not 15. Is 15 equals to 15? Yes, then we find it. So three comparisons, and that's it. And because the red black rules guarantee the tree height is always bounded by 2 times log to n plus 1, even with a million nodes, we will need at most about 40 comparisons. And that's the power of balanced tree. So now let's move on insertion. We can think of it like hiring a new employee. Every new hire start as a junior. So that's our red note. And if this creates a problem, two juniors reporting to each other with no senior between them, then HR either swaps page colors or restructures to the team, and that's the recoloring or rotation. So there's a golden rule. Also, it's very important. New nodes are always inserted as red. New roads always gonna be red. Why? Because adding a black node immediately breaks rule 5. It changed the black height on one pad. A red node doesn't affect black height, so it causes fewer problems. Let's insert 4 into a tree with 7, 3, 18. So this is our tree. So root is 7. We insert 7, it's gonna be root, and root is always black. So 3. 3 smaller than 7. It goes left. Now we're gonna add 18. 18 is bigger than 7. It goes right. But always don't forget it. First one, the root is always gonna be black. And after each inserting nodes gonna be red color. All 5 rules are satisfied at this situation. So at the step 2, we do a normal BST insert again. 4 is greater than 3. So we go right and we put 4 to the right and it's red. But now let's look at this connection between 3 and 4. 3 is red and 4 is red. 2 reds in a row. So rule 4 is violated. So what we're gonna do, we check the uncle. Uncle of 4 is not 18. So it's red. That means is case 1, uncle is red. So recolor. So we're gonna recolor it. 3 goes from red to black. 18 goes from red to black. 7 goes from black to red. So there is an issue. Root can't be red. So we're gonna change the color to black again. Because black because root must be black. So we flip it to back 7 to black. And we are done. All rules are satisfied. No rotation needed. Now that was a case 1, but there are actually 3 cases when parent is red. Case 1 is uncle is red. Just recolor. No rotation. This is the simplest fix. And when we move to case 2, uncle is black and the node forms a triangle shaped like a zigzag. For the fix it, rotate the parent first to straighten it into the lane, which converts it to the case 3. So case 3 is uncle is black and the nodes form a straight line. So for the fix it, rotate the grandparent and swap colors, and that's it. Done. This is the three cases we have to remember it. And also the key thing to remember, at most two rotations per insertion. And at most all log n recolors. Always paint the root black at the end. That's also important too. So let's move on to deletion. And now the deletion is the final boss. This is the most complex operation in red black tree, but if you break it down, it's totally manageable. So, as a real world example, we can think of it like removing a senior employee from a company. If a junior leaves, no problem, the team structure is fine. But if a senior leaves, suddenly there's a gap in the management chain. Someone needs to be promoted, teams might be need to be merged, or the whole structure needs to reorganize. And that's what deleting a deletion fix up is all about. So let's look at the phase one. Phase one is standard BST deletion. Find the node. If it has two children, replace it with its in order successor, the smallest value in the right subtree. Then delete that successor instead. After the phase one, we always end up deleting a node with 0 or 1 child. So, and now the final boss, deletion. This is the most complex operation in the red black tree, but if we break it down, it's totally manageable. So, think of it like as a real world example, we can think of it like removing a senior employee from a company. If a junior leaves, no problem. The team structure is fine. But if senior leaves, suddenly there is a gap in the management chain. Someone needs to be promoted. Teams might need to be merged, or the whole structure needs to reorganizing. So that's what the deletion fix up is all about. And let's check the phase one first. So phase one is the standard BST deletion. Find the node. If it has two children, replace it with its in order successor. Smallest value in order, uh, smallest value in the right subtree, then delete that successor instead. After phase one, we always end up deleting a node with 0 or 1 child. So in the phase two is the fix up. Three main scenarios. Let's first check the case A. Deleting a red node, this is the easiest, and just remove it. A red node doesn't contribute to black height, so removing it doesn't break anything. No fix needed, and it's done. At case B, deleting a black node that has a red child, and we have to replace the black node with its red child, then paint the child black. This is restores to black height, and that's one step and done. And at case C, deleting a black node with no red child. This is the hard one. When we remove a black node and replace it with nil, that nil position is now double black. And the path through it is one black node short. So to fix double black, we look at the siblings. If the siblings is red, rotate and recolor to convert to black sibling case. If the sibling is black, with both black nephews, recolor the sibling red and push the double back up. And if the sibling is black with a red nephew, rotate and recolor. This is the terminal case, and it always fixes the problem. So we will now see in the example, and you guys gonna understand more on the examples. So let's see case B in action. We want to delete node 10, and which is black. It has red child 11. Step 1, here's our tree. 10 is black and has child 11. And then step 2, remove 10. We remove 10 and put 11 in its place. 11 is currently red right now. So step 3, paint 11 black. So, and just like that, black height is preserved. All 5 rows are hold. So at the most 3 rotations per dilation, and the rest is recoloring. Everything stays. So all again, always. Now let's practice that our informations on the real examples. Now let's put everything together with a full worked example. So we are going to take array and insert each value one by one, showing every single fix. So step 1, we're gonna insert 10. 3 is empty, so 10 becomes the root, and root must be black, and that's done. So step 2, we're gonna insert 20. 20 is greater than 10, so it goes right. And we always remember the rule, each node we insert after the root is gonna be red. So new node is red and parent 10 is black, so there is no violation. So at the step 3, we're gonna insert 30. And when we insert the 30, 30 is greater than 20 and goes to the right of 20. And new node is red, but parent is 20 is red. It's a violation. Uncle is nil, so which counts as black. And 30 is the right child of 20, which is the right child of 10. That's the right straight line, and this is also case 2. And for the fix it, we left rotate on 10. So it's gonna be left rotated. The top one will drop and 20 becomes the root. So 20 becomes the root and 10 goes left and 30 goes right. So after that, we're gonna recolor it and then it's balanced. We have to recolor the 20 because root always is black. So at step 4, we're gonna insert 15 now. So 15 is smaller than 20 and bigger than 10. So it goes to right of 10 and it's gonna be red. So, but there is a 2 reds and it's a violation. But the uncle 30, this is the uncle 30 is red. And that's a case 1. So we're gonna recolor it. So 10 goes black, 30 goes black, and 20 goes red. So after this, we're gonna flip it 20 to black again because it's root. So at step 5, we insert 25. It's bigger than 20, smaller than 30. So it goes to left of 30. So 25 goes there. It's gonna be red. So, but the parent of 25 is 30 and it's black. So there's no violation. So there's nothing to fix. And at step 6, we're gonna insert 27. And this is a big one. So 27 is bigger than 20, smaller than 30, and bigger than 25. So it goes right off the 25. And it's gonna be red because each note we insert is red. So 27's parent is 25. It's red. 27 is also red. So there's a violation. So uncle is Neil. So Neil is black and 25 is also left child of 30. But 27 is the right child of 25. That's a left right zigzag. This is case 3, double rotation case. First, we do left rotate on 25. Now 27 is where 25 was. And then 25 drops to left and the zigzag becomes straight line, left, left. And second, right rotate on 30, 27 goes up. 30 drops to the right and we're gonna recolor the 27 black, 25 stays red. As we can see here, after the rotations, recolor it. And our final tree is 20 is the root, black, left side 10, with 15 child, it's red, and the right side of the root 27 is black, left child and the right child is also black, red. And every path from the root to nil has exactly 2 black nodes. BST order is perfectly preserved and all 5 rules hold. Okay, so we got our finished tree and now I want to find the value 25. And here is the thing about searching in a red black tree. You can completely forget about colors. Red, black, it doesn't matter at all. It's just a normal BST search. Compare the value, go left, it's smaller, go right if it's bigger. So let's try to find value 25. So we start at root 20, which is the root. We are looking for 25. Is 25 equal to 20? No. Is 25 bigger than 20? Yes. Then we go right. And we at 27, not 27. No. Is 25 equal to 27? No. Is 25 less than 27? Yes. Then we go left. We are at the node 25. Is node 25 equal to 25? Yes. Then we find it. That's it. And that's all it took, 3 steps. Right now, let's delete some nodes from R3 and we will start with 15 and first step we find node 15 in the tree. It's the right child of 10 and step 2 we're gonna check does 15 have any children and no, it's a leaf, so we don't need to find a successor or anything, we just remove it directly. So at step 3 now what color is 15? It's red and that's the key. Red nodes don't count towards the black height, so removing a red leaf doesn't change the black count on any path, so no rule is broken. So we just remove the 15 from the nodes and that's it. No fix up needed. The tree still is valid. All 5 rules hold and deleting a red leaf is the simplest deletion case. Now let's try a harder one. So at that part, if we try to remove 10, it's different than the previous one because 10 is black. So step 1, we find the node 10, it's left child of the 20. Does 10 have any children? No, it's a leaf. So again, we remove it directly. And what color is 10? As I said before, it's a black. And this is where the problem starts. When we remove a black note, the pet that used to go through it now has one fewer black note. So uh, the left pet from the 20 lost a black, but the right pet through 27 still have some count. So rule 5 is broken. So we mark the empty position as double black, as we can see here, because we remove it. And this is where 10 used to be. It needs an extra black to balance the pets. So to fix it, we look at the siblings and double black note. The sibling is 27, and is 27 red or black, and it's black. So now we check 27's children. The far nephew is 30, and 30 is red, and sibling black for far nephew red, and that's case 4. So we apply case 4 left rotate on the parent, not 20. So the 20 will drop and 27 will go up. So after the rotation, the 27 uh, takes the 20's old color black, and parent 20 is black, and far nephew 30 is black, and 25 is red. So 27 is the new root, and the black 20 is on the left and black, and 20 is on the left and it's black. And with the 25, it's red child, 30 is on the right black. Every pet has the same black height again, and double black is resolved with this case at the deletion. So that's the everything we inserted 6 values, solve all 4 insertion cases, and we searched for 25 in the 3 steps, and then we deleted the red leaf with no fix and black leaf using case 4 with 1 rotation, and every operation was all again. The 3 stayed balanced with the whole time. That's the red black 3, and that's why it used to everywhere from like Java Stream App to the Linux kernel, and that's where it is used. And thanks for watching me, and I hope this summary for this topic will be helpful for you guys, and thank you for listening me.